Hey, y'all. Today's objective is common log word problems. So we've worked with common logs and solving equations for that missing exponent or that missing expression. So today we're going to work with some word problems. If you have a exponent equation, y equals ab to the x power. A is your initial, b is that base, that percent, and then x is your time, specifically the number of times something's going to increase or decrease, and you're going to solve for x. So just a few things. We're going to use logs, we're going to use common logs, but if you have a situation where you don't have a base 10, then I'm going to show you again how to type it in your calculator to solve if you don't have a base 10. But the focus will be with base 10. A lot of writing. If a scientist counts 50 bacteria in an experimental culture and observes 1 hour later, the count is up to 100. So it has doubled in an hour. The function models the situation. So here's the equation. So in this problem, you've been given the function. P of t equals 500 times 10 to the 0.3t. So here is some sort of exponential equation. 50 meaning 50 bacteria, this is going to be your base, and then to your time. So a few questions. A, right, make sure you write all this down. What is P of 0? So P of 0, that means when t is 0. 50 times 10.30. Well, this is going to be 0, and anything to the 0 power is 1, so it's just going to be 50. And what that means is that 0 time, meaning hours, days, years, whatever, at 0 time, you're going to have 50 bacteria. So P of 0 is 50. And that should make sense because that's your initial amount. When your t is 0, when your x is 0, your initial amount is 50 bacteria. Show P of 1. So what happens at 1? That means we're going to put 1 in. So 50 times 10.3 times 1. So 0.3 times 1 is 0.3. And then I'm going to type it into my calculator. Okay, so 10 to the 0.3 power times 50 is about 99.76, so about 100. And that would make sense because 1 hour later, the count is up to 100. So at time of 1, the count went from 50 to 100. When will the bacteria reach 1 million? When will the bacteria reach 1 million? So when we're looking for the when, we're looking for this value right here. We are going to set up an equation. 1 million is our that. So 1 million equals 50 times 10 to the 0.3t. We practiced solving equations like this. You would divide both sides by 50. So I'm going to type in 1 million divided by 50, and I get 20,000. And since I have a base 10, I can use log. Since I have a base 10 right here, I can use the common log. So I'm going to take the log of both sides. And I know that it's going to give me, coming over here, something is going to equal 0.3t. So log of 20,000. And this right here, log of 20,000 is 4.301. Then we would divide both sides by 0.3. Would divide both sides by 0.3, and we would get 14.337 0.3368 years. So 14, about 14 and a third years. 14 and 4 months. Alright, and the way I did that was I looked at this equation and I substituted in 1 million for the number of bacteria, and then we solved for T. Okay, the next one. In 2000, whoops, sorry, we need to do this one first. Sorry, they were in wrong order. The world population is about 6.2 billion and grows 1.14% per year. Solve the equation to find when the population will double. So I've given you the equation and we're finding double. So if it's 6.2, it will double to be 12.4. And we're solving for the when, so that's going to be that exponent value. Here's my equation. This is my initial value, 6.2. My percent, 1.14% plus 100% would be 1.0114 to the T power. Going to divide those sides by 6.2. So that's going to be 2 equals 1.0114 to the T power. I do not have a base of 10. Notice, this is not a base of 10, so I can't just easily take the log of each side. What we can do, though, is we can rewrite it in log notation. To rewrite it in log notation, this is my base. So log of 1.0114, whoops, sorry. All right, my base, 1.0114 of 2 is equal to T. Because remember, this becomes the problem and this is your answer. So we rewrite it in log notation, and then we can solve for T. Now to rewrite this, to type this in your calculator, remember we had that conversation about do you type in the big number or the biggest value, and you're going to divide. You're going to type in the log of 2 divided by log of 1.0114. Yes. So to type this in your calculator, you're going to type in log of 2 divided by log of 1.0114. Whenever you don't have base 10, you can divide it. We can manipulate the calculator so we can get the answer. And this says T is going to be 61.15 years. All right? 61.1483. So that's how many years it will take to double the population. All right, so let me come back to this one. Okay. And this kind of is branching on the same. In 2005, it was 6.2 billion. When will the population be 10 billion? And then I've given you a different equation. 6.2, this time we have a base of 10, so our exponent has changed a little bit. Instead of it being 1.0114, we have a different exponent. When will it be 10 billion? So I'm going to replace this for 10. And now I'm going to solve. We divide both sides by 6.2. 10 divided by 6.2. And I get 1.6129. Because I have a base 10, I can take the log of both sides. And this gives me 0.005t, and then over here the log of 1.6129 is 0.2076. We will divide both sides by 0.005. And we are going to come out with 41.5215 years. So that means it's going to be 10,041.5215 years, which should make sense because the problem we just did asked for when it's going to double to 12 billion and it was 61 something years. So you know it's going to take a little bit less to be 10 billion. So we are going to work on word problems, and within the word problem the equation will either be in base 10, and if it's not, we know how to manipulate the calculator to do that, and we're always going to, not always, but we're mainly solving for the when, that exponent, that t, which stands for time.